Hey everyone, this is the second video for section 9.1 on rational numbers. So remember that last time we started talking about some concepts from chapter 2 again. So we started talking about subsets. So we saw that the rational numbers were a subset of the fractions, and we saw that the integers were a subset of the rationals. So we want to compare and look at more of these subset relations between the natural numbers that we've talked about, the whole numbers that we've talked about, and the integers and the rational numbers, right? All of these number types that we first introduced in chapter 2, we're going to talk about them again here and how they relate to each other. So there's this graphic that is commonly used in math to talk about these things. So real numbers are the only types of numbers that are the overarching number type, right? We have a number line. It's often called a real number line. If you do any more complicated math, normally in elementary school, we just talk about the number line, but it's also called the real number line because it's has every real number on it. And because those are the overarching numbers that we deal with. So the real numbers can be divided into two types: the rational numbers and the irrational numbers. So these numbers form two disjoint subsets of the real numbers, right? They're two subsets and they have empty intersections. So that means that they're disjoint. There's no overlap between them at all. And you can kind of see why this is true just based on their names, right? We have things that are rational, and then we have things that are irrational, where this prefix tells us that these are just things that are not rational. So irrational can kind of be thought of as every number that's not rational, everything that has a decimal representation that doesn't terminate, and it also doesn't repeat. So what are the common irrational numbers? So some things we've already talked about are square root of 2 and pi. Remember that pi is 3.14159, and some other things. It goes on forever and there's no repeating pattern. And it can also be decimals of the form 0.01, 001, 0001, 00001, and repeating. So even though there's a pattern here, and you should be able to tell what the pattern is I just wrote down, even though there's a pattern there, it doesn't repeat the same block of numbers over and over. So it's not repeat. Okay, so we have irrational numbers and then we have rational numbers. So rational numbers are the fractions that we typically deal with: 1/2, -3/4, and so on. The integers are things like -1, 0, and 1. Well, and 2. I'm going to go ahead and put 2 there. And 2. The whole numbers are things like 0, 1, and 2. And the natural numbers are things like 1, 2, and so on. And so you can see that they build up in a really nice way. So the natural numbers are just the counting numbers, right? You can see them on your fingers when you count 1, 2, 3, 4, 5, 6, and so on. The whole numbers, we just add 0. The integers are the whole numbers and their opposites, where we added a sign. And then the rational numbers are whenever we take integers and we make fractions out of them. And then every other number on the number line is irrational if it's not rational. And so they build in this really nice way. And so, like I said, this is a really common graphic that shows the subset containments that we're dealing with. So let's remember the notation, how we denote all of these sets. So the natural numbers are this N, the whole numbers are W, integers are Z, rationals are Q, and reals are this R. And remember that this is what's called Blackboard bold. If you're typing things, it's a lot easier. We want to just denote a capital R from the real number R and a capital Q from the rational Q. And so we use what's called Blackboard bold because if you were typing this on a computer, or if you had PowerPoint slides or anything like that, you would just use bold letters, but oftentimes math is written on a whiteboard or a blackboard or a chalkboard, and so we have to bold it in this way. And so this graphic shows us the subset containments. So we have that every natural number is a whole number, and every whole number is an integer, and every integer is a rational number, and every rational number is a real number, right? And it's represented by these nested rectangles like so. So all of these are subset containments, but we can actually say more than that, because these are all subset containments, and they're all proper. We have real numbers that aren't rational, namely the irrational numbers. We have rational numbers that aren't integers, any rational number that has a denominator other than 1. We have integers that aren't whole numbers, all of the negative integers, and we have a whole number that's not natural, which is 0. So all of these are actually proper subsets. And so we can think about them in this really nice way. There's not really a symbol for irrational numbers. Sometimes what I've used, if I need one, I always just kind of do this bolded I. Well, you kind of have to be careful to make sure it doesn't look like the Roman numeral too. That's what I use for the irrational numbers, but the irrational numbers are also a subset of the reals. That's not any sort of standard notation. There's not really a standard notation for the irrational numbers, but there it is. And where do fractions fit in here? The way that the book defines it is a little bit different than the way we've defined it. So remember in the last video, we talked about these fractions that are not rational. And we said that there's all these fractions, right? We have square root of 2 over 3, pi over 4, things like that that aren't rational, but that are fractions. And so this is where a discrepancy comes in with how I define things and how the book defines things. So the book states that the term fraction only includes the non-negative numbers, and that all fractions can be written as terminating or repeating decimals. So what the book defines fractions as, so the book defines fractions as just the positive rational or the non-negative rationals. And that's not how we typically use the phrase fraction. So I believe, and a lot of mathematicians believe, that fractions are really just defined by the use of the fraction bar, right? The fraction bar has this implied division, and that's what really characterizes a fraction. Because as we've seen, we deal with negative fractions all the time. And so it doesn't really make sense to restrict our thinking of fractions to just the positive and 0 rational numbers. That doesn't make a lot of sense with how we use the term fraction in real life. And so lots of times we say fraction to represent what we mean by a rational number or a rational expression. But this can be really confusing whenever we start introducing algebra, because when we have things like x minus 3 over x squared plus 7, x is a variable and it can have a lot of different values. So this fraction could be positive or negative, and it could even be irrational. And so it's important to understand that this terminology you use can cause confusion if you define things one way, but then talk about them another way. And that's why in this class, I don't want to think about fractions as just the positive rationals, because we don't use fractions like that. And it's too easy for me to slip up and say that things are fractions, even if it's not the way we've defined them, because that's just how we talk. So one thing that I've definitely learned through teaching is that the way that you talk about things has much greater impact on your students than I would have ever anticipated. That students mimic the vocabulary that you use whenever they're learning things. And it's way too easy to just be lazy in the way that you say things, especially in math. Math is such a precise subject that you really need to take care of the way that you talk about things, because it's really easy to confuse people if you define something one way, but then you talk about it another, because that's just how the term fractions used in everyday life. So just keep that in mind. It's definitely something that I've had to kind of adjust as I've taught. And it's one thing that you'll probably have to adjust to unless you start thinking about these things now. So the book has a different way of kind of categorizing the natural numbers, the whole numbers, the fractions, and the rational numbers. And so our way is a little bit different. This is the correct way. The book is also correct. They just have fractions somewhere a little bit different, but this graphic is much more widely used in math. This is a very standard way of thinking about the number sets. Okay, so now that we know how everything's organized, we can talk about the properties that these have. So we've talked about a ton of properties, but we're going to introduce another one, saying that a set of numbers is closed under an operation if, when you apply the operation to two elements of the set, the result is still an element of that set. So this is talking about closure. So we want to see which of the numbers that we've talked about, the natural numbers, the whole numbers, the integers, and the rationals, are closed under, sorry, this should say operations, are closed under the four main operations that we deal with: addition, subtraction, multiplication, and division. So first, let's talk about the natural numbers. I'm just gonna be a little bit lazy here and just use every symbol to talk about it rather than writing out natural numbers. So the natural numbers are just positive whole numbers or the positive integers. Remember that 0 is not positive nor negative. So let's think about the natural numbers. So whenever you add two natural numbers, right, whenever you add two positive counting numbers, you just move further along the number line and you still stay with those whole numbers or those natural numbers or those counting numbers, however you want to say it. So this is closed under addition, but then it's also closed under multiplication then, because remember that multiplication is just repeated addition. And so that's something that's really nice about the relationship between multiplication and addition, and likewise subtraction and division, is that since it's closed under multiplication, since it's closed under addition, and addition is just repeated multiplication. Wait, I'm sorry, I'm saying this incorrectly. So because it is closed under addition and multiplication is just repeated addition, it's also closed under multiplication. However, we can subtract some natural numbers. For example, if we do 2 minus 3 and get -1, well, -1 is not a natural number. So we can see that it is not closed under subtraction, and then it's also not closed under division because division is just repeated subtraction. Okay, so similarly with the whole numbers, right, just like natural numbers, if we add any of our natural numbers, we're closed. So the only other thing that gets added to the whole numbers is 0. But we know that 0 plus any number is just that number, right? Because 0 is our additive identity. So the whole numbers are also closed under addition and multiplication. But the same example works for the whole numbers. 2 minus 3 is -1, which is not a whole number, right? Because all of our whole numbers are positive. So the same example works. The same example in red over here works to show that this is not closed under subtraction and division. Okay, next we have our integers. So our integers, right, we can just think of this is just the positive and negative whole numbers and 0. So the integers, so we can, if we add two integers, we just keep jumping around the number line, right? And we just stay on every whole number, right? We just stay on positive and negative whole numbers or 0. So this is also closed under addition. So it's therefore closed under multiplication. But what about subtraction now? Our counterexample over here in red 2 minus negative 3 is negative 1. Well, that is now an integer. If we think about 2 and 3 as integers, when we subtract them, we get another integer. And that's going to happen every time, right? Whenever you subtract integers, you're just moving to the right or the left on the number line, like we talked about in chapter 8, how we added and subtracted integers. So it's also closed under subtraction. However, it is not closed under division. And that's because if we think about just 2 over 3, 2 over 3 is not an element of the integers because it's a fraction, right? It's a rational number, but we can divide these two things and they're both, honestly, they're both natural numbers, whole numbers, and integers. So this is not closed under division because 2/3, these fractions are not integers. So this is actually a counterexample for all three of these, the natural numbers, the whole numbers, and the integers. So lastly, we're going to talk about the rationals. So just think about all the things we learned in chapter 6. So we saw that when we added two fractions, we still got fractions. When we multiplied, when we subtracted, and when you divide all of these things, you still get fractioned. Right? So the rational numbers are going to be closed under all of these operations because everything we've dealt with, the most complicated thing we've dealt with is fractions. And there's no way that we can start with fractions and add in something that's irrational. There's no way to do that. If you're just starting with rational numbers, which is fractions of integers, there's no way you can get things from the irrational way. There's no way to do that when you just do those 4 basic operations. So this is closure. So again, there's examples in the book on the bottom of 331, but again, when it talks about fractions, keep in mind that that's not the way that we've talked about fractions in all of these videos. Okay, so the last property that we're going to talk about in this section is the closure of real numbers. So we see that the rationals are closed, and because the rationals fit into the real numbers, we have that the set of real numbers is closed also under all 4 operations. So this one's given to you. We thought about it ourselves, the natural whole numbers, the integers, and the rationals, but the real numbers are also closed under all 4 of these operations. So the last thing I want to say about properties is on page 332, there is a whole list of properties of rational numbers. And these properties also hold for the real numbers. So if you want a list of properties to know, I would definitely check out page 332. It has all of them listed very nicely, and it has some examples with numbers, but then also with variables where you don't have it in. So these are all of the properties that you need to know. You need to know all of these properties. You also need to know its closure property, but that's a really good place to go and look to see the properties that you need to know for the 3rd exam. Also for the final, these are all the things we've always talked about. Commutative properties, associative properties, distributive properties, identities, inverses, zero multiplication, things of that nature. You should go check that out to see all of those. So the section of the book ends just with some examples of operations with rational numbers, but like I said, we've already seen the fraction section, so we know how to do all of those operations. So that's going to be it for this section.